Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, ready to resume? Okay, so I was going through the 3 design principles of the multi-kernel model, and we're up to number 2, which is hardware neutral structure. So the idea of the model is that the operating system structure is separated as much as possible from the hardware. There have to be some hardware specific parts, the message transports and the device drivers. And one advantage of doing that is that the message transports can be highly optimized, specialized to the particular hardware, and it also means we have a lot of adaptability to change the performance characteristics as necessary. So, for example, a late bind on the protocol used to exchange messages or the transport implementation. So you might change the way in which you exchange messages, in theory at least, say if according to the workload of the machine or something like that. You could switch between a pure message passing to using a shared memory implementation, for example. The third design principle is replication of common state. So what we're saying here is that any state that is potentially shared, rather than treating it as if it's shared and having all the complexity of synchronization on that state there by default, we're saying you should treat it as if it's a local replica, as if the local core has exclusive access to that state. And the kind of state we're talking about here are things like scheduler queues and process control blocks and so on. So this naturally supports a situation where we don't have shared memory, as might be the case in a heterogeneous system, and it supports when the set of cores that are running is changed dynamically. Okay, so there's really a spectrum of replication and sharing here. So in this diagram at the top there, on the left-hand side, we've got all global state being shared and essentially one big lock. And over time, this has gradually moved towards finer-grained locking, and somewhere around there is where current operating systems are, and further to the left is where older operating systems might be. Moving towards the middle, we've got things like K42 that are recognizing the problem with locking, and then over on the right-hand side, completely distributed state and maintaining replicas, and the multi-kernel is basically coming in on the right there. And there's clearly a lot of space in the middle for different approaches as well. I'm not saying the multi-kernel is the ultimate perfect idea of an operating system for multicore. It's probably not, but it's a point in this design space. So in a multi-kernel, we have state being replicated, but we still have sharing as an option, as a local optimization. So we might have a shared replica between 2 closely coupled cores, for example, where by closely coupled, I mean if we've got hyperthreading or cores that share an L2 or an L3 cache, it might just make a lot of sense to do actual sharing there. However, because the default is not to share, then we can decide whether this is appropriate at runtime. And the basic model remains asynchronous message exchange. So just to come back to my picture, here's the multi-kernel model again. Hopefully the reasons why we've structured it in this way have become clearer from having gone through the design principles. I guess I've already said that the multi-kernel is theoretically elegant. It really is an idealized position, so it's not necessarily the way any implementation is going to turn out. I mean, for example, this message passing abstraction means that making use of the shared L2 cache it's something that we do have to specialize explicitly, rather than if you have a more pragmatic approach in your implementation, you might know that you're always going to run on one particular architecture and optimize for that, as operating systems do today. But this is the ideal. Again, just to contrast with the monolithic operating system structure. And the microkernel operating system. I mentioned yesterday a few examples of microkernels, but I probably didn't explain what a microkernel is. So the idea is taking as much operating system functionality as feasible to servers in user space. So the microkernel just does the really basic OS functionality, deals with processors and threads and memory and low-level I/O and so on. So quite often people say, isn't Barrelfish and the multikernel really a microkernel? But I think it's fairly clear that it's not. And some further reading. We're not the only research group trying to tackle the problem, the multicore challenge for the OS. And here's a few examples. Corey, Foss, Tessellation and Helios are all very different examples of with a similar approach to the multikernel. Okay, so now I'm going to move to telling you about Barrelfish, the operating system. So this is a joint project between Microsoft Research and ETH in Zurich. It's quite a large project. It was started, I guess, in 2008. And most of the stuff that goes on happens at ETH, and there's a lot of students doing PhDs and doing master's theses based around Barrelfish. So it's been ported to a bunch of different architectures, and the main paper on it was published in 2009. It was one of the references I gave in the last slide. You can download the source code if you want. It's under an MIT open source license, and there's also a very active user community. Quite a few people are interested in doing research over Barrelfish, and there's a mailing list and the occasional workshop. And there was actually a paper describing some research based on Barrelfish published at a workshop earlier this year, and I think that's and it was done by some people in Sweden, so it was nothing to do with ETH or MSR, and I think that's the first group to actually publish their research based on Barrelfish, but we're hopeful that there'll be many more. So, what does Barrelfish actually look like? So in this particular diagram, this diagram was done when it only existed on one platform, which was x86 64-bit. In the kernel, there's a privileged mode CPU driver, and this is the software that does the kind of core OS things. It enforces protection, it does authorization, it time slices processes, mediates access to the core and other hardware. It also does fast core local messaging, and it delivers hardware interrupts to user space drivers. And the CPU driver is typically invoked by a standard system call, and that has a cost comparable to invoking a system call on Linux. It doesn't share any state with any other core, so it's actually completely event-driven and single-threaded. And we claim in our papers, although I'm not sure whether this is true, that it's easier to write and debug than a conventional kernel basically because it's really small. So above that we have a distinguished user space process called the monitor, and currently the main OS state that is replicated on each core inside the monitor is something called the capability database. So Barrelfish protects resources using capabilities, and I'll talk a little bit more about that later. So one difference here from the multi-kernel model is that we've factored the monitor and the CPU driver into user space and kernel space respectively, and that's not strictly necessary according to the multi-kernel model. We could have all of the monitor functionality down in kernel space, and that would avoid some performance penalties, but we did this because we wanted to keep the kind of reflect the structure of the multi-kernel model more explicitly, but actually there's definitely a price to be paid for doing that. And obviously if we push the monitor into the kernel space, then that piece of code would become more complicated. So the monitors collectively coordinate the maintenance of global state, and they encapsulate much of the mechanism and policy that you would find in a traditional operating system. They're just normal user space processes, and so they get scheduled along with everything else. But they're very well suited to the, they're the things that are sending the messages, doing the split phase messaging, and dealing with long-running remote operations. So a monitor that has to do something expensive involving sending messages and getting replies to from other cores can send all its messages and then quiesce, and something else can be scheduled on that core to do more work while it's waiting. Yeah.
So how do these monitors are being considering that they are in user space and other user applications also can access them and they are not coming in some protection?
Right. These are distinguished processes. They do have special permissions.
So you mean to say that they are run in privilege mode, that is link 0 or?
No, they don't, but they do have, so that it all works through the capability system, and the kernel, the CPU driver controls ownership of capabilities, and so the monitor is going to be given permission to, it's going to hold capabilities that user processes are not authorized to hold. So yeah, there's a little level of indirection there. Okay, so another feature of Barrelfish that is not part of the multi-kernel model, but which turns out to be really useful, is this thing called the system knowledge base. All this stuff I've been talking about, optimizing at runtime for this and that, it really relies on having some system-wide knowledge of the characteristics of the hardware that the operating system is running on. And we do this by having this server, this essentially a knowledge base that's storing facts, either pre-loaded facts or facts learnt by, for example, measuring communication latencies at runtime. It stores all this stuff inside the system knowledge base, and we can then query the knowledge base in order to figure out how best to arrange for some operation to take place. And I will give you a concrete example of this in a bit. So the message passing, obviously it has to be fast, and ideally we do want to specialize the implementation of the message passing to the hardware. In fact, we really have to, otherwise it's too slow. But it needs to have a standardized interface. So there are two types of messaging on Barrelfish. We've got the same core messaging, which we call local message passing, or LMP, and between two different cores, which we call, not very intuitively, user level message passing, or UMP. And again, this is an aspect of the operating system where we've actually sort of explicitly implemented it in an architecture-specific way, and we package these things up in what we call interconnect drivers. So local message passing on between processes or domains, as they're called in Barrelfish, on the same core can be either asynchronous or synchronous. The synchronous version is, in fact, an implementation of a technique that somebody else devised and wrote about, Brian Bershad, back in 1990, called lightweight RPC. And it's kind of interesting, if you go and read this lightweight RPC paper, you can see that it was actually implemented on top of the Taos operating system for the Firefly, because they the claim in the paper is that this RPC everywhere was too slow, and these performance of 4,000 RPCs per second or per minute per second really wasn't good enough, and so you really needed to use this lightweight RPC. But there is definitely a trade-off between complexity and performance there, and the Firefly guys were more interested in having something that was straightforward to program. User level RPC, again, we use a technique that Brian Bershad published the following year, which I've sort of alluded to before. The message channel is a region of memory, and the messages are basically cache lines. So it's piggybacking on the cache coherence protocol, and you get really good performance by doing that, but it's kind of a low-level, grungy thing to be implementing. The replicated state inside the monitors is kept consistent using some sort of agreement protocol. So I'm going to give you a couple of examples of what we actually do. I have to say that in the context of a distributed systems summer school, these particular agreement protocols are very trivial, but that's okay. You know, we don't need to deal with things like faults in this environment, and there are other concerns. So the first one I wanted to talk about is keeping TLBs consistent. So a TLB is a cache, a CPU cache of virtual memory mappings, and when an entry in that cache becomes invalid and it has to be flushed, in a multicore system, potentially the same entries could be in other caches, and so they all have to be flushed. The second example I'm going to talk about is the capability database, which I already described, and as I said, the capabilities are used to protect resources in Barrelfish, and here we're talking about virtual memory. So to keep this database consistent requires a two-phase commit. The TLB is a one-phase commit. In future, we may need more sophisticated protocols, but so far we haven't found that to be necessary. There was an early, sort of at the beginning of the Barrelfish project, Timothy Roscoe, or Mothy, is the professor at Zurich who's leading this project, and he took great pleasure in telling people he was going to put Paxos inside the kernel. Haven't done that yet. So just to make this discussion quite clear, I'm just going to run through virtual memory at a very simplistic level, but a sufficient level to understand what I'm talking about. So memory is divided in most machines into fixed size blocks called pages, and the user process can have a virtual memory address size that is much larger than the physical address space. when a page is mapped, as we call it, its virtual address is translated to a physical page address so that the page appears in physical memory. This allows lots of different processes to have pages in memory at the same time. It means that pages are specific to a process, so they can't access each other's pages. And it allows the physical pages, the pages in memory, to be moved around completely transparently to the process. So this means that pages can be loaded anywhere in main memory. It doesn't have to be fixed. This level of indirection helps that, and the fact that the memory is broken up into these fixed size blocks means that it doesn't have to be contiguous. The pages can be scattered throughout. So here's a picture I stole from a book by Patterson and Hennessy, showing basically pictorially what I've just told you. We've got the virtual addresses mapping to physical addresses. When a page is not in physical memory, then it's on backing store, on, for example, a disk. So page tables are what hold the mapping from virtual to physical addresses. So when the data that a process needs to access in memory has to be in its page table. If the page isn't in if the page isn't in physical memory, then there has to be a fault generated in order to pull that page from the backing store into memory. And there's a valid bit in the page table that indicates where the page is at the moment. And these page tables are themselves stored in memory, and there's a register that points to the page table for each process. And the operating system will modify each the page table of each process as necessary. Okay. So the TLB, the translation look-aside buffer, is, as I said before, this very small CPU cache of those recently used address mappings from virtual to physical. So, actually, I'm just going to go back up to here. There's something I forgot to say to you. So, no. Okay. So, the trouble is that overhead of page translation is, if there isn't a TLB, then it's actually really slow. And in fact, as virtual memory sizes get really large, we end up with, for example, multi-level page tables are pretty standard. So this means that it can be very expensive to look up the address translation. And so that's why a TLB is really important. And they're small. They're typically 64 to 2048 entries. And on each memory reference, the CPU will compare the page number from the virtual address with the set of pages in the TLB, and it does all of this in parallel, so it's really fast. And the hit rates on a TLB are typically 95% or more. Okay, so whenever this page table mapping changes, the TLB has to be flushed. So this happens, for example, when there's a context switch, when one processor is swapped for another, or also when the status of a given page changes. So again, another helpful diagram from Patterson and Hennessy showing what happens. The virtual page, the page is first looked up in the TLB very fast, and if there's no hit, then it has to go through to the page table, of which there may be more than one. There may be multiple levels. Okay, so this flushing of the TLB is often referred to as TLB shootdown, and that's what we call it in the Barrelfish paper. And it will involve the TLB of every core that might contain the same mapping. So the way it has to be done is that the core that wants to flush the TLB sends a message to all the other cores and waits for a response. In Linux and Windows, what happens is the core will send an interprocessor interrupt and then wait for some counter to be incremented, some shared counter. In Barrelfish, the monitor does this, and it performs this one-phase commit. And what I'm going to show you is how it can exploit knowledge of the topology of the interconnect and the caching hierarchy to improve the performance. Okay. So the hardware that we're using for this experiment is this weird AMD Opteron that I showed you before, with the huge disparity in communication latencies between different pairs of cores. Okay, so the first implementation that we did of TLB shootdown was pretty naive. So the way it worked is there was a single broadcast URPC channel, so a single messaging channel. And if you remember, the implementation of URPC, of the messaging between cores, is basically piggybacked on the cache coherence protocol. So the actual behavior that arises as a consequence is that every slave, every remote core, ends up polling the same shared cache, waiting for the master to modify it. So there's one cache line which is going to be updated by the master, and all the other cores are going to be watching for changes to that cache line to see when it changes, and get their TLB shootdown message. The problem is particular to the cache coherence protocol in AMD 64s, because when the master updates its line, immediately that line is invalidated in all the other caches, and all the slave cores then have to pull the new copy from the master's cache. So with n cores, you're getting this cache line crossing the interconnect n times, and we see that latency grows linearly with the number of cores. I'll show you a graph in a minute. So maybe a bit better to do unicast, to send a message to each other core, but do it point to point. So now that the cache lines are only shared by 2 cores, it's better, but it's still linear. So here's the messaging costs. Latency in cycles times 1000 on the y-axis, and cores on the x, and the top line is the worst case, the broadcast. But we can do better. We know that those Opterons have a shared cache on chip shared by cores. It's the level 3 cache. So the cache lines that are shared by those groups of 4 cores won't cause any interconnect traffic, and be a lot faster. So we use a 2-level multicast tree for shootdown messages. Send a message to the first core of each processor, which then forwards it to the other 3 cores in the package. And that second message is a lot faster because of this shared L3 cache. And also, all 4 processors can be sending messages in parallel, and there's no interconnect contention. We can actually do even better than that, which is to use the fact that the machine is NUMA, and there's, as we saw before, the different latencies between pairs of cores. So why don't we choose to send to the remote, the single core on each package? If we choose the ones that are the furthest away with the highest latency and send their messages first, then the whole thing will happen even faster. Here's a picture of that actually happening. So this is a tool that we wrote. Actually, we've reused it over and over again for many projects. But it's basically sucking on events that are being generated by whatever system we're monitoring, and then we just have time going along the bottom from left to right, and in this case, each line is a core here from 0 at the bottom to 15. And we instrumented Barrelfish to produce an event on message, send, and receive. And you can see that the core at the bottom, which is the master, is sending. First of all, it sends to 3 other cores. Those are its local cores, and it also sends to cores on different packages. And I think you can, if you look at it carefully, you can see what's going on with the hierarchical forwarding of the messages. And so the costs when we do this are substantially better. The bottom line is the NUMA-aware multicast, and it's almost flat with the number of cores. And the multicast, actually the steps in the line correspond to the fact that we've got this latency problem, and we're not overlapping the way that we are when we go NUMA-aware. So this is making use of specific knowledge about the architecture that we happen to be running on, and but doing so in a way that's not, we haven't designed the operating system to do this all the time. This is done in response to a runtime query to the SKB to say, hey, what are the communication costs between these different cores, and what's the caching hierarchy, and so on, and then using that information to decide what the best way is to issue messages for TLB shootdown. And so it can be done differently for a different architecture. And then just another graph showing the end-to-end comparative latency of the TLB shootdown. So Barrelfish has a fixed overhead, which is more expensive when you have a smaller number of cores, because it has to do a local, send a message to the local monitor, and there is, as always, a per message cost of marshalling, of some demultiplexing, and there's various scheduler effects. We're also measuring it here on a version of Linux and a version of Windows, and there's the error bars are showing the standard deviation. So the reason that Windows and Linux perform worse as you have more cores involved is because of serially sending interprocessor interrupts to do the shootdown. Okay. Are there any questions? Yeah. Could you speak up, or is the microphone around?
My question is, why would multiple processors do the sharing entire listing? Why do you need to slow down entire PNG instead of invalidating a shared entity?
The TLB is per core.
TLB is per process, right? Per core.
It's per core, and they're not sharing any state. So the processors or domains have the same virtual address space. So if the mapping changes and you don't update on every core, then that the process running on that core could potentially go to the wrong page. Does that make sense? Well, we can talk later if it's still confusing.
How does Barrelfish manages this across heterogeneous code? The example that you showed was for, I think, NUMA.
Yeah.
So I think as the architecture changes, I think the way paging and TLB is handled, that will also change for different codes.
Yes,
So
I think you're right. The answer is I don't know.
Since one of the claims is that it works for
Yep. Well, I think in recent work that they have actually done some work on heterogeneous architecture and got Barrelfish running, but I don't know what they did specifically because that was after I stopped working on the project. But actually, Tim Harris, when he arrives, Tim's been working on Barrelfish right up to now, so he would be a good person to talk to about the more recent stuff. But it's a great question. I mean, yeah, there's a lot of, we have this sort of nice idealized stance on how things should be structured, and then we go in and try to actually implement it, and things don't necessarily work out the way that we hoped. And yeah.
And that's a user address.
Yeah.
Not your monitor, not your server.
No.
So if you have a heterogeneous code,
Mm-hmm.
I would have first write an application that will run on heterogeneous code before we have to worry about CFD as well. CFD shootdown across heterogeneous applications.
Mm-hmm.
That's sort of inherently hard problem. I don't know how to write a process that will run on multiple code.
Yes.
Right.
Agreed.
So I think that's a good question, but I don't know how you, under what circumstances you need to do that. Like you need one address space that runs on x86 and big engine machine or whatever, right? That's not that easy. So the B system used to do this. You didn't talk about it.
No.
It had two different binaries. So when you did process migration, it would run a different binary on different machines. So I don't think
Like that's a CUDA program or something like that, which makes use of CPU as well as GPU. So it has different instruction sets for both the both the devices which are currently heterogeneous, but still then.
but there's still one address space. That's the only problem we have, right? We need a single address space for which we have cache translations in CPU. If you have two address spaces, then this is a no. I don't know enough about CUDA, but if you think you're going to have one address space that spans GPU and GPU, then yes, I think you might have that problem. Sorry, I don't mean to laugh with it.
For GPU, I don't think you have a single config. The part which gets executed in the GPU is the very nice.
Yes, I think you have MAC address space, right? It is MAC, right?
No. Your some sort of communication or memory as okay,
Okay. All right. So the second example of an agreement protocol in Barrelfish is the capability database. So basically, regions of memory are protected by these capabilities, which have types. Obviously, they can't be forgeable, and user domains keep track of their capabilities in this data structure that we call a C-space. Capabilities can be turned into capabilities of a different type according to a set of rules, and capability can be split up into a number of smaller capabilities. So, when a program starts, it's given a region of address space, and it can then subdivide that address space, and it can do different things with different parts of it as it needs to. So monitors keep track in the capability database of who owns which capability and what type that capability has. And these capabilities can be copied around the system. So you can have multiple copies of the same thing existing. And a capability can only be, capability of one type can only be converted into a different type once, and it can be revoked, although, again, revocation is a very tricky problem, and I'm not convinced the Barrelfish implementation tackles that well. Okay, and these databases are kept consistent using a simple two-phase commit. So what might go wrong that's bad? So say Core 1 acquires what we call a RAM cap. A RAM cap is the raw region of physical memory. It's the capability for a region of physical memory. It passes it to Core 2. So Core 2 now has that. In the meantime, Core 1 turns that raw memory capability into a frame capability. This is basically physical memory that can now be mapped into the domain's virtual address space. So it's basically giving it a piece of memory that it can now use. And it maps it. In the meantime, Core 2 retypes this capability to a C node type. And a C node is a region of memory that's designated as a place for storing capabilities. And now Core 2 passes that region back to Core 1. And now Core 1, in theory at least, can fabricate arbitrary capabilities just by writing bits to its innocent frame capability, which has actually been turned into also a kind of privileged C node region, which is used for storing capabilities. So this is a way of compromising the protection that the capability system is supposed to be offering. So we really need to make sure that when a capability is retyped, that retyping takes place on all of the cores absolutely for certain, and that there's no possibility that this can happen. This was actually, it says demo there because this was actually part of a live demo that we used to do. And so here's our hardware again. It's the quad-core AMD Opteron. And here's the what happens if we do this as a two-phase commit, sort of naive unicast using our visualization tool from before. So you can see pretty clearly Core 0 sending a message to every other core and waiting for a reply and so on. And then doing it again, and the total time is about 100,000 cycles, which is not great actually. And again, we did exactly the same trick that we did before by making the consistency, the capability database protocol NUMA-aware. So once again, we're exploiting the architecture that we happen to be running on, and same thing. Core 0 sends a message to some core on each of the remote packages, and then they forward locally. And so now we get loads more overlapping, and it's much faster. We've reduced the time by 30% or thereabouts. Okay, so just to move to a slightly different mode, to finish this talk, and I might even finish early, it's very exciting, I just wanted to talk about the challenges of implementing Barrelfish on Multicore, and actually I think these apply to the implementation of any software on Multicore. So as we all know, good performance comes from getting lots of concurrency and being able to communicate between the cores very quickly. But concurrent programming is problematic. It was quite remarkable how much deadlock, for example, we ran into coding Barrelfish. It's really hard, even though this was done largely by the students at ETH, who are really smart and they really know what they're doing. Furthermore, it's really important to be able to identify the bottlenecks, and that's not always straightforward, and also providing the right APIs so that people can actually do this kind of programming without their heads exploding. In this message passing scenario, actual sharing of data can be expensive, and as I sort of started with at the beginning of this talk, caching is great, but it doesn't scale. It does need hardware support. So moving to the multi-kernel model, we're reducing contention by replication and partitioning, but we're paying the price of having to run these agreement protocols and have all that additional latency and complexity at a different level. So to make this concrete, here's a programming example, and this was an actual fairly trivial example that we ran into as part of developing Barrelfish, but it makes a kind of interesting case study, if you like. So this is some pseudocode showing what happens if you want to start a domain, a user program, on multiple cores. And you can think of this as like starting a bunch of affinitized threads in some other system. So the lines 1 and 2, for I is 1 to the number of cores, create a new thread on that core. And then wait until some counter called NUM-threads gets up to the number of threads that we want. While that counter is not at the number of cores, we're waiting for the next message and doing something about it. The next message in this case will be the remote core saying, I'm done. So each core sends, I'm done. And when that happens, handling that message involves this invoking this function thread create callback, which just increments that counter. Okay, seems really simple. What could go wrong? So here's our visualization tool again. So the first implementation of this was really awful. 40 milliseconds. I mean, this was pretty bad. We put in loads of instrumentation. You can see the key at the top. I don't expect you to be able to interpret this in any way. Obviously, it's impossible. But we had events for lots of different activity going on inside Barrelfish. The monitor working, the monitor blocked, the monitor polling, the monitor setting pages to 0, running the actual application, which was called spantest.exe, the name service, the memory server, all this stuff. And what we found here is that what's actually going on was that the domain spanning was basically the memory system was being used a lot. The memory server was being used a lot, and everybody else was essentially blocked. There's a lot of light blue there showing all the monitors were blocked. The brown sort of almost vertical lines are messages being exchanged. There's quite a lot of them, particularly going down to core 0, which is where the memory server was running. So we didn't have I don't know if this has changed recently, but at the time we only had centralized memory server. So this memory server, this is OS. A lot of OS services are running as servers, and so we had one memory server because it seemed like a good idea at the time. And when a new domain wanted some memory, it had to send a message to the memory server. So we had one of those, and it was running on core 0. So it was obvious from that previous visualization that the memory server was the bottleneck, which is kind of odd because you don't really think of memory allocation as a potential bottleneck on the critical path of creating what is essentially a bunch of threads. But that's what we ran into. So we basically ran a memory server on each core and gave it a static partition of the memory. The idea of a partition memory server is great in theory, but in practice it's kind of an interesting open research question. I mean, how should you divide up the memory? How should you do load balancing? Should you have a NUMA-aware hierarchy of memory servers? How and when do we adjust the amount of memory that each server has? And what are the overheads in the long term of doing that? But anyway, for the purposes of making domain spanning fast, we just did the very basic thing. And we also improved our implementation of memset, which was found to have some performance issues. So now we got down to 9 million cycles from 50 million down to 9 million, which was substantially better. But still, not really good enough. So we went back and looked again. So the monitors were using the centralized memory server, so we made them use core local memory servers as well, and we actually moved B0 off the critical path. Oh, and now we're down to 4 million cycles. Like, it's just somewhat surprising how much performance improvement you could get. Even better, change the API. So this was done just for the purposes of seeing how much better it would be. We haven't changed the API, but if you create the domains all in parallel, then suddenly you're sending a whole lot less messages, and we get down to 2.5 million cycles, approximately 1 millisecond, which, yeah, that's probably acceptable for this operation. But it was, you know, a non-trivial amount of work to get to this point, and in fact, at the time, Barrelfish didn't really support doing it this way, and it wasn't obvious to us, you know, that this nitty-gritty of designing your interfaces to deal with this kind of operation is not necessarily obvious when you start. And in general, as I said, it is actually pretty hard programming with messages. I showed you Andy Tannenbaum's comment yesterday that we should all avoid asynchronous message passing like the plague. So Tim's lecture on Friday, assuming it happens, he's going to talk about something called asynchronous C, or AC, which was developed as part of the Barrelfish project. It's extensions to C to do non-blocking I/O, and it actually helped quite a lot. So for further reading, basically, please go to the webpage and check out what everybody's doing. It's a pretty active project, and if it appeals to you and you want to get involved, there's lots of room, lots of nice projects, you know, lots of stuff to do. The credits for Barrelfish: bunch of people at ETH, bunch of people at MSR. My conclusion, which you can probably already guess. Machines are like networks. For good performance, we need to pay attention to the things that distributed systems designers care about as well, which is basically fast messaging, using replication, and paying attention to latencies. And we believe that we should be able to take ideas from distributed systems and apply them in the operating system. And that's the end of my talk. Are there questions? Robert?
So you said you were going to give us an example of constraint solving where you...
Yeah, I forgot that I'd taken that slide out. I'm sorry. I can show you later. It's just a line of prologue. It's basically figuring out the NUMA-aware, the TLB shoot. Actually, I don't even remember which of those two examples it applied to, but it was basically asking the system knowledge base about the intercore latencies and using that to decide. I can certainly show you later. There's actually a paper in ASPLOS done by the guys from ETH, which is about using the system knowledge base to program the APIC stuff at the beginning, at boot time. Yeah.
Just regarding TLB shootdown. So, is it that when you want to see the process, and the process might have multiple threads, how to invalidate the TLB of the code in which the threads of the process is running, and you need not invalidate TLB of the code in which the threads of a different process are running?
Yes, in theory, yes.
But what happens in Barrelfish? I mean, the TLB, like someone pointed out, is more or less like a local thread.
Yeah, I don't actually know the answer to that question. I think in Barrelfish we just invalidate all of them. I mean, is that what you're asking, whether you selectively invalidate? Yeah, I don't know. And I don't know what normal operating systems do. Does anybody know? No? Okay. Sorry, I'd have to look that up. Yeah. That would be nice. So the yeah. Yes. 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 So actually, when we started the Barrelfish project, we originally envisaged this. You know, we should build a distributed operating system. Nobody's done it, and you know, we really need one because it's kind of tedious not having one when you have a lot of, especially now, we all have so many devices and computers, and you know, why can't they be integrated at that level? But it turned out that just looking at the multicore thing constrained us. But you're right that there's certainly scope to push it out and see if there's something we can do that might make sense. Although my intuition is that you actually want to use higher level software rather than operating system level. But maybe sending messages makes that wrong. I'm not sure. Sorry, I can't hear. Yeah, yeah, yeah. It would be a really interesting thing to try and do. Yeah. Any more questions? Okay, thank you.